slideshow. Right, just to confirm, you can all see that?
Yep, absolutely.
Fantastic. So, as my very good friend just said, I am involved with the area of news, media, and that kind of stuff. Mitch Electronics is currently shut down, but going to restart soon because of COVID. The shortage of semiconductors that I'm sure you're all aware of caused a lot of problems, and basically I couldn't get my hands on half the parts I needed. So hopefully I can restart that one. So really this presentation is more of a rant at the engineering community than it is you know, sort of like sort of things you typically see in these things. Basically, as an engineer, especially someone who does a lot of maker stuff, whenever I look at code examples or when I look at new microcontrollers coming out, it's amazing how often the documentation for this or the code examples tend to be complicated, convoluted, or sort of very obscure. And so basically the idea of this presentation is to try and show some examples of bad documentation, show examples of what documentation should look like, and then to try and get engineers to appreciate how their customers are not them. So one thing I've always found, especially with my father isn't a mathematician. He's very, very brilliant. He's very, very clever. The problem is when he was teaching me maths at home, he assumed that I had the same level of intelligence as he did, which was not true in that case. And so he never understood why I didn't understand the things he did. Now, that's not to say he wasn't a good teacher, but because of that, he wasn't able to recognize that the person he was teaching wasn't as good as he is. And so that you tend to see this in engineering, where they may write some documentation or code examples and they're not entirely clear, and it makes it difficult to get into something that's quite advanced. So to start off, let's just look a bit at how hardware has changed over the years. So going back 20, 30 years, when the first microcontrollers and the first microprocessors came out, they were very, very simple. They had small memory sizes and their peripherals were limited. And that basically meant that understanding the entire workings of a microcontroller was very easy to do. So you take something like a PIC16 chip and it's very easy to understand the entire thing, whether it's the UART, peripherals, SPI, I2C, how the oscillator tuning bits work. You can program these things in bare metal. You can go right down to the assembler level. You can program bank switching, and it all makes sense. And it's very, very simple. But as technology progressed, things got more complicated, including things like DMA. You had things like very advanced sort of UART systems that had lots and lots of registers, all able to configure it in different ways. And because of that, it became quite difficult to interface with all this stuff. And a good example are modern ARM microcontrollers. Now, you can program these things on the bare metal in assembler, but it's not a very good idea to do so because they are very, very complex. And trying to do the most simple program can end up needing hundreds of lines of assembler code just to get the peripherals correctly initiated. And so that's where we see high-level languages, things like C, C++, Python. So the idea of these languages was to essentially simplify the coding stage by creating some level of abstraction between the processor and the code. So in the case of C, we don't have to worry about particularly how memory is allocated by the compiler for variables unless you're doing something specific. You can allow the compiler to sort of do all that yourself. And so what that means is you don't have to worry about how the CPU registers are doing stuff. You don't have to worry about what the peripherals are doing because there's some kind of API wrapped around in C that handles all of that functionality for you. And so that is essentially what the goal of high-level languages are in modern microcontrollers and computing systems, which is why you never ever see assembler code in modern PCs. You never really see it now in microcontrollers unless you're doing something really, really specific. And these types of high-level languages also make multitasking a thing as well. You know, it makes it much, much easier. So give you a funny example, actually, I'm currently designing a Z80 computer for a bit of fun, and I've actually made it into a multitasking system. But the amount of complexity and involvement with registers is just unbelievable. You have to know where every single register is going, where the variables are being stored in RAM, and it's just a massive task. But if you did the same thing in C, someone's made a library already for it. You can stick it in, and it's a case of just writing a bunch of functions and sticking them together. So high-level languages allow us to abstract these very complex microcontrollers. And now this is where the rant starts, why many APIs suck. So when you look at a lot of modern microcontroller platforms, I tend to find that a lot of the APIs are absolutely terrible. And the reason why I say these things are terrible, it's not that they're functionally bad, it's that their documentation is often really bad. And then sometimes the code names or the function names given for these APIs are also pretty difficult to understand. So to give you an example of, sorry, I should mention very, very quickly that I've got a bunch of examples of bad APIs and bad documentation, but I would like to stress that that's not to say that the products are bad, but that they could be improved. So I'm going to mention a few products coming up. So I'm not saying don't get them. What I am saying is that the people who design those should probably consider the engineer who's going to buy them soon. So this is a really funny example of how code examples and APIs can be quite bad. So take an example of hang on, is it? Let me just check if it's here. Is it? Yeah, here it is. Perfect. Okay, brilliant. Right. Sorry about that. Yeah. So the first example we're going to look at is Bluetooth. Specifically Bluetooth as a UART connection, which you can do with certain libraries. So here is the Arduino code to make that happen on an ESP32. This is an excellent example of what an example code should look like. It's about 30 lines of code. That includes white space. It's commented, and it's very, very simple. The function names are very simple, and it's easy to read, almost like a piece of English. It's just written in plain English, and it's very easy to understand. But now let's compare this to the Nordic Bluetooth serial example that comes with the NRF 5340 in their Visual Studio Code example. This is the first 30 lines of code, and we've just included a few libraries. We're still 250 lines in, and we're doing some kind of memory allocation that's not commented. A few hours later, after going through the code, and we get down to about line 627, and that is the equivalent example on the NRF 530 by Nordic Semiconductor compared to the ESP32 on the Arduino IDE that did it in 30 lines of code. Now, in my opinion, this is unacceptable. If you're going to make an example that's just to send a few bytes over UART, just to show the user how it works, having 600 lines of code with comments sparsely put around, in my opinion, is going to send makers over the edge. And so I thought we would look at a second example, which is to do with the STM32 range products and how they have some issues in terms of trying to convey information and trying to make their platforms easy to use by makers and engineers alike. So in the case of STM32, things have changed recently, but for the past few years, if you wanted to learn how to use the STM32 devices in the STM32Cube IDE, it came with a lot of problems, and it was mainly to do with the fact that the online tutorials were very sparse or poorly written or all over the place and fragmented. And it took me a very long time to figure out all the little tips and tricks to getting it to work. So the Arduino IDE can program STM32 devices, but it hides the peripherals of the STM32, which is why I've always wanted to code it in the native STM32 IDE. But I did find eventually one video series that sort of demystified it perfectly, and it went through. The guy who actually made the video wasn't even a member of STM32. He was a maker of his own, and he sort of figured out all the little things you need to know about the integrated development environment to figure out how to make it to work. And after studying his video, and I realized all the little things that I was doing wrong that weren't clearly explained on online tutorials, basically made it very difficult for me to use it. So again, it is a good IDE, but there are lots of things that it doesn't mention. And one of those, which was quite annoying, was the fact that you had to configure the SWD pins. And I can't go through the example now, but basically there's a small little option in the pin mapping that you have to select. And if you don't select it, you can only program your device once before it can't be programmed again. And that's because it doesn't understand that. It basically, I think it switches those pins from being programming pins to sort of like digital I/O pins, and then thus it can't communicate over those pins, which is very, very important, but it was never clearly explained online. Another few little things that irritated me were things like that register bit definitions had already been shifted, but it hadn't been explained. So, for example, bit 7 wasn't accessed using the number 7. It was accessed using something like the number 80 or something, because that represents the highest bit in an 8-bit number. And there was also another one, which was that the system peripherals for debugging had to be enabled by the user, but were not enabled by default. So if you didn't enable that, you couldn't debug, but it wasn't clear that it couldn't be debugged. So again, this is an example of poor documentation and poor examples of how to use their products, which made it hard for people like me to get into this. So again, we go back to the Bluetooth example for the ESP32 in the Arduino IDE as being an excellent example for software. And again, it comes down to a number of things. The online tutorials for it are very, very good. They're numerous and they're very, very clearly explained. The many comments on the code also helps to describe what's going on. And the use of clear English in the function calls mean that it's very easy to read and understand what's going on. So if we look at the serial print function, this is just an example of how the API for the Arduino IDE is just brilliant. So when you go on the official website for Arduino IDE and you look up serial print, you get a whole bunch of stuff about how it works and examples of how it works. So it doesn't just show a function with some sort of describing what it needs. It actually shows an actual code example of what it would print. As we can see down here, serial.print in brackets 78 gives 78. It's very, very simple. It's very easy to understand, and it clearly shows what the function is doing. Now, an excellent example of online documentation would be the W3 Schools website, which teaches people how to code things like HTML, JavaScript, and CS. And what's really nice about their website is that not only are things clearly explained, but they have a really nice layout for the website, and it's very, very clear and very easy to follow and understand, and everything's in order. I do tend to see some tutorial websites for some products for engineering parts sometimes can be a bit sparse or fragmented, or in other cases, you might find that it uses a very old system or an outdated system, so it's difficult to navigate. And another example of excellent online documentation is Blue Wireless. They have these products called note cards, which are cellular devices that are a system on module, and you only have to communicate over them through a serial port using JSON code. But one thing that's really nice about their website is that not only is it clearly labeled and very well presented, they also have an inbuilt terminal on their website as well. So you can put in commands for your connected device into their website, and it will communicate with your note card over USB. And even better, the code examples they give on their website can be directly downloaded to the note card, so you can confirm that your thing is actually working. And each function is clearly described, and it's just an excellent example of what documentation should look like. And so now we are going to move over to APIs as opposed to documentation. So documentation is about describing, what it is that you built or what your product is and how it works. But APIs are the actual sort of software library that you're using to interface with what it is that you've created. Now, this table here shows sort of a quick comparison between what a good API function name would be and what a bad API function name would be. So things like the Arduino, they use things like send byte, read string, Wi-Fi connect, kernel restart. These are good API function names because it's obvious what they're doing. If we look at the equivalent, that I have seen these in quite a few open source libraries. I have seen these in libraries for microcontrollers sometimes, and they use API names that it looks like they're trying to cut down on the size of the function in terms of the number of characters used to represent that function. but it doesn't help the coder. It doesn't help make it readable. So I've seen, for example, K reset as kernel reset. I've seen that before, and it's obvious when you know what it is, which it would be obvious to the original engineer who designed the API. But if you're new to the API and you see that in a piece of example code, it's not entirely obvious what it's doing. And so I think the most important thing when it comes to API function names, they have to be readable English. And when it comes to code examples, comments are absolutely everything. And it's amazing how often I see example code not have enough comments. So one thing I've seen some coders say is that you can have too many comments, but I completely disagree, because comments enable for any programmer to look at your code and understand exactly what is going on. But of course, comments are a double-edged sword, in that if you write a comment that's incorrect, that describes something incorrectly, I would argue and say that is probably the most dangerous line of code you can ever write, because you may write a library that's got a bug in, you have a comment that describes what it's doing, but the comment is wrong, and then someone's trying to debug their code and figure out why it's not working. They would look at the comment and assume that the comment is correct. And so it's absolutely essential that you comment your code, but at the same time, you make sure that the comments are accurate. So to give you an idea of what I believe is a good piece of commented code, is something I've done recently in assembler myself. Almost every single line is commented, and not just a comment in the way that it's like, oh, load A with B or something. It's almost written in sentences. So as you read the code, it makes sense. So starting from the top, step 2 and 3, get task and store into reg table. Now we need to store all the data. And it just means that it's easily read, and whoever wants to pick up this piece of code, who's never seen it before, would understand what's going on. The function names and the variable names are given English names. They're not given something that's abstract or bizarre. They are readable, so it's obvious what's going on. So load A with current task on line 85 is pretty obvious what it's doing. Now here is an example of assembler code which I pulled from online that doesn't explain the code as well. So for example, large portions of this code are uncommented, so it's up to the reader to decide what's going on. Overall, I have no idea what this code is actually doing. There's no big block of comments at the top describing this piece of code in depth, what's going on, where it's located. And the use of absolute addressing in places makes it impossible to figure out where the first place jumps to in the code. And it's also interesting how the use of IO addresses has also been numbered instead of labeled. And again, that makes it difficult to figure out what the code is actually trying to do. So now the point of this presentation was really to sort of demonstrate to engineers the problem with bad documentation, the problem with bad APIs, and how it can affect the people who use your products. Because at the end of the day, when you code something, when you write a piece of documentation, you know everything about it, but the person who's going to pick up that document doesn't. And if you assume that they know what you know, they won't know what's going on. So how does this relate to the RT thread community? So I was asked to do this presentation about a month and a half ago about giving my thoughts on documentation and if anything could be done in the RT community to improve what it's done. Now, the good news is I've actually looked over the RT thread IDE and the documentation and the examples, and I'm very, very impressed with what's been demonstrated. So to give you an example, I was able to download the IDE in about 5 minutes. I installed it, I connected my ST-Link to it, then an STM32 device. I opened up the Blink example, programmed it, and it worked first time. No complaints, no issues. And this is really, really important, because unlike the STM32Cube IDE, which took me days to figure out, or worse, the Nordic NRF Connect platform, which I'm still struggling with, the RT Thread platform worked first time with no complaints. Now, the really nice thing about using a custom IDE that RT Thread does means that I don't have to try and install tool chains and mess with compiler settings, which is something that you have to do with a lot of other platforms, especially the Nordic Connect for, I think it's called Connect for Desktop. You have to install SDKs and point to the right location in your editor. Otherwise, you can't compile with it, and that makes it really, really difficult to work with. So the RT-Thread IDE is a bit like the Arduino IDE. You can just download it, get examples running and working in minutes. The online documentation for RT-Thread is somewhat easy to follow, but what I find is that advanced topics are introduced a bit too soon. So, for example, I was looking up the introduction to what RT-Thread is, and within the first few paragraphs, it was already talking about advanced kernel functions and processes and how it multitasks and all that kind of stuff. And that's all good, but it's not needed for someone who just wants to get started. The only thing that someone needs to know when they first start using RT-Thread is, how do I compile my first project? How do I get into the main part of code? And how do I blink an LED? How do I connect to a button? How do I connect to GPIO? How do I connect to UART? And it should get progressively more advanced from there. Another really nice feature I found of RT was that the function names are really, really good. While they do use RT underscore at the beginning, I like it because it makes it clear that it's an RT-Thread function. And what I was really happy to see was that there were no function calls that were obscure or unusual that I didn't particularly like. I think there may be one or two, but the vast majority of them were really, really good. So I'll give you an example of one thing which I didn't like was the virtual file system function, which is dfs underscore make dir. Now, the only reason why I know that it makes a directory is because I've seen that before in terminal code. But dfs, I have absolutely no idea what that meant at the time. And so the virtual file system, calling it dfs underscore make dir, I just kind of felt it's not exactly clear what it's doing. So, for example, I felt like a better function name would be something like underscore new directory or new folder, because it's very obvious what it's doing. And the RTK printf is another one of the things I didn't like at all, because it just feels a bit messy. It's hard to read and it's a bit confusing. And this is another example of why writing a clear API is important. So I feel like, for example, RT underscore kernel print would be a better version of that code. So additionally, I also felt that some of the examples for things like I2C were a bit complicated, not because the code itself was complicated, but the example pages were a little bit complicated. They're quite in depth, and there's a lot of words, which is why one of the first things you should be doing in a basic example is showing the most simple piece of code needed to make something happen over I2C. So even if it's just something as simple as writing a byte and opening a device, and it's only maybe 5 or 10 lines, that should be the first thing that's demonstrated in your documentation. You shouldn't jump into things that are advanced before that. But overall, I've found that comparing to all the other RTOS solutions I've seen out there, RT-Thread is definitely one of the best. And I feel that it comes down to the nice API, the good documentation. Now, it could be improved in places, but generally speaking, the documentation is very, very good, certainly better than others ones, which I've been told not to mention, Zephyr. But generally speaking, it's very simple, and the use of a dedicated IDE makes things a lot easier to work with. So just to sort of summarize, hardware is becoming more complex, and the software that goes to that hardware will undoubtedly get more complex. We're looking at AI now coming onto microcontrollers. We're looking at advanced systems coming onto microcontrollers. We're looking at Linux coming, or Linux as some people pronounce it, coming onto basic microcontroller projects. And when that happens, things are going to get very, very advanced. And that means we have to use APIs for them. And when this happens, when engineers start making more complex APIs for more complex functions, we need to think about how the end user is going to look at that and see and think if they will be able to understand it. Because at the end of the day, when you make something new, when you write a new API, when you write a new piece of documentation, the person who's going to be reading that is not you. It's going to be someone else who has no idea whatsoever about your system, about your code, about your device, about your API. And so when you write examples, when you structure tutorials and lessons, you have to treat the engineer as if they're completely clueless, and start from basic principles and work your way up. Pardon me. Now, that's why I kind of prefer the top-down approach. So you can start from the bottom up. You start with the most basic things and then move your way up. But working from the top down, especially with examples, might make it easy to understand. Now, what I mean by working from the top down means start with something that's very, very simple, but fully functional. And then sort of break it down into things that you may need eventually. So let me give you an example. You may take something like a Bluetooth UART project. At its most basic, what it needs is to be able to transfer some data across Bluetooth. So it shouldn't be more than a few lines of code, and that should be a working example. But if you want to start teaching the user about multitasking or context switching and all this kind of stuff, that's something that must come later, and you work down into it. Pardon me. And I think another thing that could be quite useful for engineers to do is to remove as much setup code as possible and get your example to work in the fewest lines of code. So if we go back to that Nordic example with the Bluetooth, and it was like 600 lines of code, most of that was setup code. And a lot of that is not going to be useful to the person who reads it, because A, it's not described, and B, it's doing a lot of stuff in the background that the user doesn't really need to know at that point. And so if that code can be shifted to an external function that just hides it all from the user, I believe it makes it a lot easier to understand the example, which makes it less frightening for engineers, which makes it easier for them to understand, and it gets people using your projects and your software and APIs much faster. So I think that is the end of my presentation, and thank you very much for having me on this conference, and I shall now pass it back over to our host.